Okay, so welcome to section 1.2, the domain and range. The domain and range, once again, this is material that should be review. And range. So the first thing I'm going to do is interval notation. So interval notation. Do I want to call it interval? Oh, okay, so I think I'll do it this way. So we're going to look at the graph. Then we're going to look at interval notation of that graph. Interval notation. And then we're going to look at set notation for the same interval. Okay, so let's consider just values of x. So what I'm going to do is I'm going to give us little x graph, just the horizontal axis. And let's say I have a solid dot at A and a solid dot at B. And I want to consider the region between the two. So if I'm looking at all values of x between A and B, where A is included and B is included, then in interval notation, what that looks like is bracket at A, because A is included, and comma, bracket at B, because B is also included. So we have, for an interval notation, we use brackets to indicate the equal sign, the solid dots. Now set notation, on the other hand, would be curly bracket, the set of all values of x, and such that, in this case, is just a straight up and down line, such that, and we can say x is between, so is an element of, the interval will be now from A to B. So notice I'm still using the interval notation within my set notation, but set notation adds the set of all x's such that. So that's all we're doing to go from interval notation to set notation. Okay, so let's do another one. Oh, is this not going to work, maybe? Oh, no paste. Okay, why is my thingy not working? Okay, weird. I had copied it, but I guess it doesn't want to work anymore. Okay, then I will just draw another one. So now, here we go, x. Let's copy this. Copy. Okay. Hopefully it'll work this time, but with my luck, probably not. So now let's say I've got a solid at A, but now let's say I have an open dot at B, meaning I don't actually get there. So I want to consider the interval between A and B, only now B is open, so I can get very close to B. I just can't actually arrive at B. So the interval notation for this will look like closed bracket at A, because I can get there, but open parentheses at B, because I can't actually get there. Okay, so set notation would be the set, so curly bracket is read aloud, the set of all values of x given, so straight up and down line, given x is an element of, so x is an element of the interval, including A, but not including B. So a square bracket at A and an open bracket at B. Okay, let's see if it'll allow me to paste. Yeah, there we go. It's going to allow me to do it this time. Oops, let's move this up one. I don't need that much space, but I think you're getting the idea here. Let's say we're open at A, closed at B. The definition is analogous, except now I'll have the parentheses at A. So this will look like open meaning parentheses at A, bracket at B. So I cannot include A because it's open there. I don't actually get to A, but I do get to B. Okay, so set notation will be the set of all values of x given that x is an element of the interval from A to B. Not including A, but including B. So a square bracket when I include. So A and B. Okay. Now, what's the next possible variation on this theme would be they're both open, right? So I have an open dot at A and I have an open dot at B. And I consider the interval between them. So now I don't have square brackets at either end. I just have open brackets. So I feel like I'm going to sneeze, so I'll say Gesundheit or excuse me ahead of time. Pardon me. Excuse me. That's what happens when it's all smoky outside and everything's on fire. Okay, so now we have open brackets. So now set notation would be curly bracket, the set of all values of x, given that, so up, straight up and down line, given that x is between A and B. Now, both I cannot equal either A or B. Because it's an open dot, I can get very close to them, but I can't ever equal them. That would be a closed dot, so there we are. Okay, so the other types of intervals are ones that go off towards the infinite. So now we still have A and B. So we still have a solid dot at A, maybe a solid dot at B. But now what we're going to do instead of the interval between them, now we're going to consider the interval that goes off towards the infinite in either direction. Okay, so going to the left of A, reading from left to right, the leftmost value would start at negative infinite, and then it would come all the way up to A, and I would have a square bracket at A because I can actually equal A. There's a solid dot. But then I would union that, starting again. The next place my interval begins, where yellow begins, is at B with the square bracket. I can actually equal that. And then going farther to the right, I go all the way to positive infinite. And because we can never arrive at infinity, we have open brackets. So now the set notation would be, there's a couple ways we could do this. I'm going to write it as a set of all values of x, such that we can say x is, shall we say, less than or equal to A, because it's pointing to the left of A, or, and for those of you that know set notation, or and union, which is what we have here, are the same thing. Or x is greater than or equal to B, meaning pointing to the right of B. So greater than or equal to B. So that's how we, oh, that's a terrible B. Here we go, B. So there we are. And the rest are defined analogously, right? We could define open at one end, closed, etc. So I think you get the idea. So let's recall. So recall. So number one, the domain of a function. So the domain, that's what we're recalling. So the domain of a function, is the set of all inputs or all allowable inputs. So is the set. Notice I'm using the word set. So it's like I'm going to be using set notation for the domain, and I am. So the domain of a function is the set of all allowable inputs x. Okay, so whereas the range of a function, so the range of a function we're also going to use the word set. So is the set of all values, is the set of all values of y attained by the function over its entire domain. So I'll just say over its domain, meaning it's implied that it's its entire domain. Okay, so let's note one thing before we begin with an example. So note. So when finding the domain of a function, finding the domain of a function, if we can reduce this does not exclude the restriction on the domain for those values of x. So this will make sense once I actually put this into practice. So for example, or actually before I do that, let's recall one more thing. So recall. So a couple things I want to recall. So thou shalt not divide by 0. Shalt not divide by 0. Next thing is, pardon me, is how should I say this? The domain of even indexed roots. Is greater than or equal to 0. And that pretty much covers everything that we need to worry about. Dividing by 0 and making sure that whatever's underneath a square or even indexed root is greater than or equal to 0. So for example, find the domain of the following functions. So find the domain of the following functions. Okay, so number 1, let's say we have that f of x, is equals to 1 over, and let's do x squared minus 2x minus 3, say. Okay, so let's look at this function. So we have that f of x is 1 over the quadratic x squared minus 2x minus 3. So I'd like to factor this. So this will be 1 over. So what two numbers multiply to negative 3 but add to negative 2? So I claim the two numbers that multiply to negative 3 and add to negative 2 will be negative 3 and positive 1, because negative 3 plus 1 is negative 2, and negative 3 times 1 is negative 3. So therefore, I know that x cannot be, because thou shalt not divide by 0. I know that x cannot be 3, because 3 minus 3 would be 0. And I know that x cannot be negative 1, because negative 1 plus 1 is 0. So therefore the domain, the way I would write the domain for this function, is the domain. Why am I having so many issues? How do I write the domain? It's a terrible D. There we go, that's better. So the domain will be the set of all values of x, given that x is not equal to 3, and x is not equal to negative 1. So that's how we could, not equal to negative 1. So that's in set notation how we could write the domain of that function. Thou shalt not divide by 0. Okay, let's do another one. So number 2. So let's say now we have that f of x is the square root, which is an even index, 5x plus 30. So since it's square root, and 2 is an even number, let's look at this. So we have that f of x is the square root of 5x plus 30. We know that what that means is that 5x plus 30 is necessarily greater than or equal to 0. So now I can subtract 30 from both sides. I'll get that 5x is greater than or equal to negative 30. Then I can divide by 5, which means x is greater than or equal to negative 6. So the domain of this function is going to be the set of all values of x, given that x is greater than or equal to negative 6. There we are. That is the domain in set notation. Let's do another one for good measure. Number 3, third time's a charm. So we have that f of x is equal to the quotient. In the numerator, we have x plus 2. And in the denominator, we have x squared minus 9x minus 22. Okay, so let's look at this. We have that f of x is, in the numerator, x plus 2. And in the denominator, we have x squared minus 9x minus 22. So our goal is to find in the denominator two numbers that have a product of negative 22 but have a sum of negative 9. Okay, so 22 is really 2 times 11. So if I have negative 11 and positive 2, if I add those two, I get negative 9. But if I multiply them, I get negative 22. So notice that I could reduce x plus 2 into x plus 2. But my domain must exclude even that which I can reduce. So you might think, oh, the domain is simply x cannot be 11. But even though I can reduce it, the original function is not in reduced form, which means I have to keep the x cannot be equal to negative 2 as part of my domain. So therefore the domain of this function will be the set of all x's, values of x, given that x is neither 11 nor is it -2, regardless of whether I can reduce. Okay, so that's a caveat we need to keep in mind. The reduction does not change the domain. Okay, so let's note. So let's say I want to find the domain and range graphically. So note. So in order to find the domain and range graphically, so in order to find the domain and range, graphically, domain and range graphically, we can project the shadow of the function on each axis. And I'll show you what that means. So we can project the shadow of the function onto each axis. Okay, so what does this mean? So for example, so let's find the domain and range. So the domain and range of the following. Okay, so number 1, x and y coordinate axes. X and y. Let's do 1, 2, 3. 1, 2, 3. 1, 2, 3. 1. Okay, so let's say I have a graph that looks something like so. Let's say I have an open dot at 1, 3, closed at 2, 0, and closed at 3, 2. So let's say I have something that looks, well, that's terrible. Let me make this look a bit better. Maybe something like, what is that? Why can I not draw what is going on here? Something like so. Good enough for government work. Ugh, my goodness, come on, I can do this a bit better. Okay, so here is my function. So I want the domain to be that which I project onto the x-axis. So if I put a shadow onto the x-axis, this function is going to have an open dot here at 1, but then a solid dot here at 3, and it'll be everything in between. So this is 1, 2, 3. So the shadow that this function makes on the x-axis, which is the domain, in interval notation will be open at 1, but bracketed at 3, because I can actually get there. Now let's look at this same shadow cast onto the y-axis. You might say, oh, well here, but actually this whole thing is a shadow. So the shadow cast onto the y-axis, if I were to shine a light, it looks like the range goes from 0 at the bottom, but then goes all the way up to 3 at the top, but I cannot include 3, right? So this is 0, 1, 2, 3 on the y. Agreed? So that is our domain and range if I cast a shadow onto either axis. So number 2, let's say we have x and y coordinate axes. Something that looks like so, which is a graph we will get to in a moment. So let's say we have something that like this, and we have asymptotes. So we have vertical asymptote and horizontal asymptote. So if I look at the shadow cast onto the x-axis, thou shalt not cross a vertical asymptote. So it looks like the shadow cast onto the x is everything except 0. So I would say that the domain will be from negative infinite to 0, non-inclusive. Then I start again, so union. I start on the other side of 0 and go all the way to positive infinity, reading from left to right. But notice that if I project the graph, the shadow, onto the y-axis, since there's a horizontal asymptote here, I know it's open at 0, but it casts a shadow onto the whole y-axis. So the range is going to be not including 0, but all the way upwards to positive infinite. Let's do one more for good measure. So number 3. Let's say we have something like x and y. So 1, 2, 1, 2, 1, 2, 1. Oops. So we have a solid dot here and something that looks like so. Why am I having such issues drawing a nice curve? Why is that so difficult? So I'm going to put an arrow going to the left, but it stops here on the right. So if I look at the shadow cast onto the x-axis, I know it's solid, but then it goes all the way to the left forever because of that arrow. So the domain from left to right on the x-axis is from minus infinite all the way up to 2. Because of course this is 1 and 2 on the x-axis. Now let's look at the shadow cast onto the y-axis. Well, I'm solid here at negative 2, but then because of the arrow, it's going to go upwards forever. So the range starts on the y-axis at negative 2 with a solid dot, but then increases forever. So this was negative 1 and negative 2 on the y-axis. So hopefully this is making sense. Okay, so the next subtopic I'd like to cover in this section is called piecewise defined functions. So I'm plotting piecewise defined. Piecewise. I don't know if it's hyphenated. Maybe it's not hyphenated. Piecewise defined. There, that's hyphenated there. Defined functions. Okay, so number 1. The first thing we want to do is list all graphs, or yeah, okay. So list all graphs as distinct. The English. What to do with English. So list all graphs as distinct functions. Number 2. So now we're going to plot each distinct function as a dashed line, with dashed lines. So plot each distinct function with dotted lines. And then last but not least, fill in each function. So fill in each function on its given domain. Okay, so what do I mean by this? So let's see. So for example, so plot the following. Plot the following piecewise defined functions. Piecewise defined functions. And state their domain and range. And state their domain and range. T-H-E-I-R, E-I-R, domain and range. Okay, so number one, let's say we have that f of x is defined piecewise, meaning there'll be multiple pieces. The first piece is negative x squared plus 3. And the domain will be x between negative 2 non-inclusive and 1 inclusive. The next will be 2x, and the domain for that will be x strictly greater than 1. Okay, so the way we want to do this is look at two different functions. So I'm going to call the first one f sub 1 of x. That will be negative x squared plus 3. And the second one will be f sub 2 of x, and that'll be 2x. So I'm going to plot both of these functions, dotted initially. So x and y coordinate axes. X and y. So 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So if I were to plot negative x squared plus 3, it's an upside down parabola shifted up 3 units, or I could plot points if I didn't know what it looked like. You can always resort to plotting points. So it's an upside down parabola. But I'm not going to fill it in because I don't know what the domain is just yet. Oh, that's terrible. Okay. Then my next graph is 2x plus 0. So my y-intercept is 0. My slope is rise 2, run 1. That's going to look something like so. So now what I'd like to do is look at the domain for each. So I know for the first graph, x was between negative 2 and 1. So that means that between negative 2 and negative 2 open and positive 1 closed, I can draw the graph. Because that's the domain, meaning the values of x that I can plug in. So let's make sure we know that that's negative 2, negative 1, 0, 1, and 2 on the x-axis. Okay. And now for the second function, x is greater than 1. So if I look at the x-axis, I go up to the second function. It's greater than 1, so it's open, and it's everything to the right. So there's an arrow there. So notice now my graph is that which is solid. So that's the graph of this piecewise defined function. But now what is the domain? So if I look at the domain, if I project to the x-axis, looks like it's everything to the right of negative 2. So I claim the domain of this function does not include negative 2, but goes all the way to the right because of that arrow. Whereas the range looks like it intersects here at negative 1 on the y-axis. But if I look at the shadow, it appears to shade everything upwards. So I claim that the range of this function is not including negative 1, but everything above it. Okay, so hopefully that's making sense. Actually, let me move this over. Don't need to use that much room. Okay, so let's do number 2. So what do we have? We have, in this case, that f of x is equal to the absolute value of x from which we're subtracting 2 for values of x between -1, non-inclusive, and 3 inclusive. And let's have it just be x squared for values of x less than or equal to -1. So once again, let's look at this as two functions, f sub 1 of x, which is the absolute value of x, minus 2. And if I look at the second function, f sub 2 of x, which is just x squared. So let's plot those both. So x and y coordinate axes. X and y. So 1, 2, 3, 4. 1, 2, 1, 2, 3. 1, 2, 3, 4. Okay, so if I were to plot the absolute value of x minus 2, that's a v shifted down 2 units. So it would look something like so, dotted. I have to do it dotted until I know what the domain is. Okay, then x squared is a parabola at the origin, opening upwards. I could plot points. Remember, if I don't know what it looks like, feel free to plug in points until you do know what it looks like. You'll get used to these functions. So here is my dotted version of x squared, the quadratic or parabola. Okay, so now for the first function, my domain was values of x between -1, so open at -1 on the graph would be here, and closed at +3. So remember, this is corresponding to -1, 0, 1, 2, and 3 on the x. So that means I can plot solid dots, between these two values. Okay. And next we had the domain was x less than or equal to -1. So on the graph of purple, we have a solid dot where x is -1, and then less than or equal to means everything to the left forever. So there's an arrow there. So let me draw that a bit better. Corresponding to the intercepts. There we go. Well, you got the idea. Not that great. My drawings are just terrible. Okay, so now let's look at the domain. If I project either onto the x-axis, I'm going everything to the left, and I'm going to the right only to 3. So it looks like my domain will start at -infinite because of the arrow on the purple part, but then it stops at 3 for the blue guy. And the range looks like it goes down here to -2 and goes all the way up. So it looks like the range includes the point at -2 on the y-axis and then goes up forever. Okay, so this is -1, -2. Okay, let's do one more, shall we? Looks like one more will fit. So 1, 2, 3. So let's say we have that f of x is equal to, what shall we do? Let's just do the square root graph for values of x between 1 and 4. And let's do, once again, x squared for values of x between -2 and 1. Okay, so let's look at this. So we have f sub 1 of x is just the square root of x. Then we have that f sub 2 of x is x squared again. X and y coordinate axes. X and y, let's see, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4, 1. Okay, so the square root of x starts at 0, square root of 0, square root of 1, square root of 4. So it looks something like so. And x squared, of course, is a parabola at 0, 0. Or a quadratic equation. Looking something like so. Okay. So now let's look at the domain. For the first function, I have a solid dot at 1 and an open dot at 4. So a solid dot at 1 and an open dot at 4. Remember, that corresponds to the values of x. So 1, 2, 3, 4. So we have this portion of that graph. And now for the purple guy, the parabola, we have x between negative 2 and 1, neither which is solid. So negative 2, negative 1. So that means an open dot here on the graph at negative 2 and an open dot here on the graph at 1. Remember, those are values of x. So therefore, plotting in just between negative 2 and 1 gets us this graph here. So that's the entire graph. So notice if I project down onto the x-axis, it's open at 2, then open at 4. So I claim the domain, if I look at the shadow cast, will be from negative 2 to 4, not including either endpoint. Now if I look at the projection onto the y, it looks like it's open up here at 1, 2, 3, 4. But then it's solid all the way down to 0. So the range starts at 0 and goes to 4, but does not include 4. Okay, so hopefully this is making sense, and I'll see you guys in the next video.